Hello again. This is the video on chapter 10. We're going to talk about these sections in chapter 10. If I could do it in one video would be great. Otherwise, maybe in 2 or 3 videos. See how long we can take to go over these. I hope you're doing well. So let's get started. So what I'm going to do is I'm going to run this PowerPoint for the first time, and I have to, maybe this is good. I guess we can see it. Yeah, okay. So what we want to do is we want to talk about conic sections. Conic sections are created by two right circular cones like these that basically share this tip, right? And a plane goes through these, intersects it, and depending on the angle of the plane that intersects this and where it intersects it, we get different intersections. For example, if a plane goes through with this angle there in one of the cones, then we get an ellipse. If it intersects us in a kind of a horizontal way, not slanted like that, then we get the intersection is a circle. And if it goes through both cones, maybe this way, so it goes through both of these cones, then we get something called hyperbola. And if it goes through one of the cones, then and it comes out this way instead of staying within the cone, right? See that? If it comes out that way, then the intersection would be a parabola. Now, it is also possible to get 3 shapes that are called degenerate. So these are degenerate shapes. If the plane goes through exactly that point, so intersection would be just a single point. If it goes through so that it just touches the cones here, then the intersection would be just a line. And if it goes through, cuts through the 2 cones and the center goes through, then the intersection is just 2 intersecting lines. Now, to get a kind of a feel of what I mean here, we're going to just do this animation, not that one, but the other one here, online, and see what this thing actually looks like. So I'm going to do one at a time. So let's say, for example, this is when we get a circle. Let me turn this off so we can only see one plane. So as you see, this blue plane or green intersecting that, and you see the intersection is a circle, right? All right, so let me turn this off and go to hyperbola. So this is hyperbola. As you see the plane intersecting going through both of these, and we get a shape called hyperbola. See that? That's a hyperbola, and you can see it right there. Okay, and here when the intersection is an ellipse, as you see, as a plane and going through the cone, intersection is an ellipse. And here is a parabola. See, a plane cuts through the cone and then comes out this way and is a parabola. Okay, here is the situation when we get 2 intersecting lines. You see the two intersecting lines. You see that one and this one. As you see, that's 2 intersecting lines. See, so the plane has gone through the center and the 2 cones, and that's why we get 2 intersecting lines, as you see. Okay, and single point, see, the plane has gone through just one point, and that's a single point. And degenerate conics here, which is actually a line, see, is touching only, see, the two cones right there and right there, and the intersection is a line, as you see. See that line right there? And then the rest of it is, of course, right there in the back. See, that's the line. Okay, so hopefully this gives a better visualization of what we're talking about here. All right, so let's start with ellipses, and that's where the book starts with. So we're going to start with ellipses. So if you put two fixed points in the plane, and then look for points in the plane such that the condition is that the distance from the point to these two foci, so we call them foci, is a plural of focus. So each of them is called a focus, and one of them is, of course. So this is a focus, and together they're called foci. Now, if we guarantee that the point is such that the distance from the point to this focus and the distance from the point to this focus, the sum of these distances remains the same. Now, if you go all the way all over the plane and find all the points that can satisfy that condition, then we have an ellipse. So if you can actually draw an ellipse this way, put two pins on a piece of paper, and then a piece of cardboard, and then get a string with any length, and then connect them to the two pins, and put a pencil there and pull it so the string is not loose, and then keep pulling it and turning it around. By doing that, you actually find what? Everywhere you go here on this, everywhere you go, the sum of these two would be just the length of the string, and obviously if you keep pulling it, the length of the string doesn't change all the way around. So basically what you do, you find all the points that satisfy that characteristic that we just talked about. And you can actually draw an ellipse, right? All right, so let's talk about some vocabulary. This point is called the center of the ellipse. As you notice here, one side is longer than the other one. So the axis, these are called axes. So the axis that is longer is called the major axis, and the axis that is shorter is called the minor axis. These 2 points are called, of course, foci. This is focus, and this is another focus. And then these 2 points are called vertices, like the vertex of a parabola, but this has 2 vertices. So 2 vertices, 1 center, 2 foci. And then these 2 points on the shorter axis are called co-vertex. So these are co-vertices, and these are vertices. So vertex is always on the major axis, and also foci are on the major axis. The 2 co-vertices are on the minor axis. So let's see if we can get an equation for it. Now, by convention, if the ellipse is horizontal like this, and in this section we're going to talk about horizontal and vertical ellipses. At the end of the section, we're going to talk about how is it possible to have ellipses that are diagonal. Okay, and that's by rotation of axes. We're going to talk about that at the end of this chapter. Okay, so horizontal, then the major axis would be this way. This would be the center. These are the foci, and these are the vertices. right? Which is the picture here. If that is the case, the distance from the center to a vertex is called A, and the distance from the center to a focus is called C. So you see that's C and that's A. And the other one is called B. So this distance to the co-vertex is called B. Now, if the ellipse is vertical, like this, then if the ellipse is vertical, then the center is here, the foci are going to be here, the vertices are going to be here. Now, again, this distance here is called A, this distance here is called C, right? And this distance here is called B. So if it's vertical, A is always the distance on the major axis. So if the major axis in the direction of Y, then that's where A goes. And if the major axis is in the direction of X, that's where the A goes. Okay? All right, so how do we write an equation for this? Well, remember for a circle, to find an equation for a circle, we put the center in the middle of the plane, and then we found points that are the same distance from the center, and we came up with what? X minus h squared plus y minus k squared equals to r squared. Now, in the equation of a circle, if you divide everything by r squared, what do you get? You get x minus h squared plus y minus k squared equals to, well, divided by r squared equals to 1, right? And this is the form that we are going to follow to write equations for ellipses, hyperbolas, and even parabolas. So circle we already know. This is the one you learned in algebra. If you divide by r squared, it's going to look like that. So the right-hand side is always 1 here. We're going to follow the same kind of strategy to find equation for an ellipse. So one thing, first of all, notice here is that it's easier if you put the center at the origin, right? And then find an equation for an ellipse. And if we wanted to move it somewhere else, it's easy. You just add and subtract numbers to x and y coordinates, and you can move the center, right? So we're going to derive the formula, the equation, from this situation where the center is at the origin. So we put the center at the origin, right? Now, first of all, notice this point right here, right? Let me go back. I lost my pen. So this point right here, think about this point, is on the ellipse, right? So it's supposed to satisfy the characteristic that the distance from this point to this focus plus the distance from this point to this focus has to be constant. Now we want to know what that constant is based on the naming that we gave to these distances. Remember, we call this distance A, we call this distance C, and we call this distance B. Now, what is the distance from here to here? Well, the distance from here to here would be the distance A plus the distance C, right? So the distance from here to here would be A plus C. What's the distance from here to here? Well, distance from here to here would be this distance, which is A, minus this distance, which is C. So it would be A minus C, right? So that's that distance. If you add these two, what do you get? You get the constant, right? And if you add them, notice that we get the C's cancel, So we get 2a. So that means in this situation, and with the naming that we have, the constant that the sum of the distances is always equal to is 2a. So 2a is the constant we are looking for. Okay? Now we're going to look at another point which is going to be helpful because it's going to give us the relationship between these letters A, B, and C. So we go to another point on the ellipse, which is that one. Again, that point has to satisfy the characteristic that what? That the sum of this distance plus this distance has to be 2a, right? But notice that since this is actually symmetric, this side is equals to this side. So the two red segments are equal. But we also know that the distance from here to here plus the distance from here to here has to be 2a, right? So let's write that. So what's the distance from here to here? Well, that distance would be from C0 to 0b, right? From C0 to 0b. And that distance would be given by distance formula, right? x2 minus x1 plus y2 minus y1, right? So y2 minus y1, x2 minus x1. And then the distance from here to here is given by this distance formula. And if we add these two, we should get 2a, right? But since these two are the same, so the red segments are actually equal. So if the sum of these two, let's call it, whatever this is, let's call it the height or the length. So that's length, that's one, that one is L, that one is L. So we know L plus L, which is 2L, has to be 2A. So 2L equals to 2A. So that means L has to equal to A, right? If you cancel the 2's, L has to equal to A. So that means this distance from here to here is A, right? But in this right triangle, A squared is B squared plus C squared, right? So we found the connection between what? A, B, and C in an ellipse, right? So if the ellipse looks like this, then this is A, this is B, right? This is A, and the C is right about here, right? Now realize that this, if you connect from here to here, that also is A. So A squared equals to C squared plus B squared. Now if the ellipse is vertical, we are going to use the same idea. Again, this is, we're going to call this distance A, right? And this distance here is C, right? And this one is B. And the same relationship exists. All right, now that we got that under control, now we can go to any point on the ellipse, like for example this one, and then write the formula based on xy. So we write xy because xy could be anywhere. So what's the distance from here to this focus? Well, that's the formula right there. And what's the distance from here to this focus? That's the formula right there, right? Again, x2 minus x1, x2 minus x1, y2 minus y1, right? Squared. And now we have to do some algebra to simplify this. And it requires like a page of algebra. So I'm just going to show you, I'm not going to do it here, just show you, you can do it yourself. You have to move this square root to the other side and square both sides and then do it again to get rid of both the square roots. But let's see what we get if we do that. I said one page of algebra, I wasn't lying. Actually, it's one page I divided into two. So as you follow here, you can easily follow yourself. You can stop it and follow, stop the video and follow this. So you see, we move this to the other side. square both sides, and we isolate the square root one more time and square again, and we are going to end up with something like this right here. Now we are going to, so based on our relationship between a squared, b squared, and c squared, we know b squared is a squared minus c squared, right? Remember we said what? We said c squared is a squared plus b squared, right? So b squared is c squared minus a squared. So if we assume that b squared is a squared minus c squared, then, I wrote it in a wrong order. So a squared equals to b squared plus c squared, right? So based on this relationship, and let me go back and make sure I wrote it here correctly. Yes, I did. So a squared equals to b squared plus c squared. Remember, in an ellipse, right, we said that this is b, right, and this is c, and we assume and we prove that this is a, right? Remember? So this is a squared, which is the hypotenuse, squared equals to b squared plus c squared. Okay, so if you move the c squared to this side, we get this. So in this formula, instead of this, all this, we just put b squared. Instead of all this, we just put b squared. And then, now we divide everything by a squared, b squared, to make the right-hand side 1. Then we get this very famous formula for an ellipse that goes through 0, 0. Okay? All right, as I said, you can stop this and look at the algebra. So we got two formulas. Here is a standard formula with the center HK and a major axis parallel to the x-axis. So remember, if the center is at 0, 0, right, we just have x squared over a squared plus y squared over b squared equals to 1. So a is in the direction of major axis, which is horizontal in this case. Now, if we have vertical and the center is at 0, 0, if we have something like this, again, we write x squared over b squared plus y squared over a squared equals to 1. Again, a is in the direction of y now, so we put it under y. And here a is in the direction of x, so we put it under x. Now, you can see easily where these come from. All you have to do is just move what? Move the center to HK, and that's how you get. In transformations in algebra, you learn that if you subtract something from x, right, and from y in an equation, then you move to those points, right? So the center is going to be HK, and that's the formula for horizontal ellipse, and this one is for vertical ellipse. All right? So the values a and b determine how far in the x and the y direction, respectively, one counts from the center to arrive at points on ellipse. So for example, if you want to graph something like this, x squared over, let's say, 9 plus y squared over 16 equals to 1. Well, which one is a here? This one is a, because is what? Is the bigger one, right? So now, this is a vertical, right? The center is going to be at 0, 0, because h and k are 0. And then x tells you how far, this number tells you. Now remember, this is what? This is a squared. This is b squared, I meant. And our a squared is what? Is 16. So b is 3 and a is 4. That means in the direction of y, we go up 1, 2, 3, 4. That's the vertex. We go down 1, 2, 3, 4. That's the vertex. And then we go right and left 3 units. So we go left 1, 2, 3, and and we go left 1, 2, 3. You can draw a rectangle here. This is called the guide rectangle, like that. And then you draw your ellipse in here, like that. That's the graph of this ellipse. Again, remember, the bigger number is your a. In this case, a is what? A squared is 16. And don't forget, these are a squared and b squared. Okay? That's the idea. And then to find the focus, where the focus is here, we know what? We know that a squared equals to b squared plus c squared. So we have a squared, which is 16, and we have b squared, which is 9, plus c squared. So c squared is going to be 16 minus 9, which is 7, right? So c is the square root of 7 plus and minus. So we go up. Square root of 7 is about what? 1 point something up. Square root of 7, 2 point something. 2 point something right here somewhere. Graph that's about right there. That's one focus, and you go down that many. Square root of 7, and that's another focus. So you can find the foci once you have your C. Okay, so here is an example, right? So the center of this is where? Is at negative 1, 2. So we go to negative 1, 2. That's the center, right? Now again, this is a vertical, so this is our A. So A squared is 25. So A is plus and minus 5, right? That means from the center, remember this is under Y, you go up 5, right? 2 plus 5 is 7, so you go up there. And you go down 7, 5. 2 minus 5 is negative 3. And then this number tells us that B is what? Plus and minus 3. So we go right 3. Negative 1 plus 3 is 2. And we go left 3. Negative 1 minus 3 is negative 4. And we draw our guide rectangle. Then graph the ellipse. Now, to find the y-intercept and x-intercepts here, you can easily set x equal to 0 and solve for y, and set y equal to 0 and solve for x. Now, if you don't want to find it, just draw, do your best here, but don't put any numbers here. The numbers that you put here should be only the numbers that matter, which is that one and that one. So leave this empty, so you can actually cross at any point you like, right? So nobody's going to tell you it's wrong or right. And because we can't find out, right? Now, the only numbers you should put here are what? C now. Now, what is C? Where are the foci here? Now, once we graph the ellipse, now we got A and B again. We know A squared equals to B squared plus C squared. So what is our A squared? Is 25. That's important to get A and B correctly, otherwise in this formula it's not going to be correct. That's our A because it's the bigger one. So A squared is 25 equals to 9 plus C squared. So C squared equals to 16, right? So C is plus and minus 4. So from here, 2 plus 4 is 6. So that's one focus right there. And then 2 minus 4, 2 minus 4 is negative 2. So that's another focus. So now we got the complete picture of the ellipse, right? All right. And that's how we get the C's and the focus, the foci, right? And the major axis is there, and the minor axis is going to be here, right? If you're asked about co-vertices, they're right here, and the vertices are right there. And you can give the coordinates of the vertices. This vertex is at negative 1, 7. This vertex is at negative 1, negative 3. You can also give the coordinates of the foci if you're asked. All right, so here's another one. It says, find the equation of the ellipse with foci 2, 1, 4, 1, and vertex at 0, 1. So we're going to graph these. 2, 1, here's one foci, one focus, and 4, 1 is another focus. And we are given one vertex. And notice the foci are sitting here horizontally. That means A here is in the direction of X. And this is one vertex, right? So we know that the other vertex will be on the other side, right? Because the foci go in the middle of two vertices, right? So now we know the center would be between the foci. Now what number goes between 2 and 4? Well, 2 plus 4, 6 divided by 2 is 3. So the x-coordinate of the center is 3, and the y-coordinate is the same as those, right? So the center here, the center, which is HK, equals to 3 and 1, right? And our A here, what is it? The A is the distance from one vertex to what? To the center. And that distance is obviously 3, right? 3. So A is 3, right? So that means A squared is what? Is 9. Now we know what C is, right? We know what C is. C is the distance between what? Between the center and one focus. That's C, which is 1. 3 minus 2 is 1. So C is 1 and A is 3. So we know that A squared equals to B squared plus C squared. So B squared is going to be A squared minus C squared. So B squared equals to 9 minus 1 squared, which is 1, which is 8. So B is plus and minus the square root of 8. So we know A squared is 9, and B squared is 8, right? And C, we have it already, is 1 here. But we need those two to write the equation, right? And we need the center. And this is in the direction of X. So what we have is X minus what? X minus 3 squared over, remember, A is in the direction of X. So A goes here. So over 9 plus Y minus 1 squared over what? Over B squared, which is 8, and equals to 1. So that's the equation of this ellipse. We don't have to graph it. If you were to graph it, you have to put another point here, the vertex. So vertex is 3 units to the left here, 3 units to the right, we'll end up at 6, right? So that's another vertex. And then you can go up square root of 8 and down a square root of 8 and draw your rectangle, guide rectangle, and graph it. But we don't have to graph it here. We just had to to find the equation. So let me erase everything here and show you this is the same kind of stuff I just did. You can read through it and make sure you got this. So let's continue. All right, now there is a number called eccentricity of an ellipse, denoted by E. Eccentricity is the distance from the center to focus, which is C, right? Divided by what? The distance from the center to a vertex, which is A. So for ellipses, the eccentricity is C over A, right? Now notice this is the center, and this is the vertex, and the focus is somewhere over here. So, and this one right here, again, this is the center, and this is the vertex, and focus is somewhere over here, right? So focus would be closer to that. Now, if you think about C over A, you see that the ellipse above on the left has an eccentricity of almost close to 1. Why is that? Because if you stretch the ellipse further and further, the focus is going to go towards here. So the focus for this would be right really close to what? To that. So C is almost equal to A. So when you divide C divided by A, you get almost a number close to 1. So E for ellipse goes from 0 to 1. The closer this is to 1, then the more stretched the ellipse is. The closer E is to 0, then the more circular the ellipse is. For example, for a long time, people thought that we go around the sun in a circular path. But what happened was that the observations didn't match a circular path. So Kepler and others realized that the path is not circular, but is elliptical, where we are almost like this, is even closer to a circle, and the sun is basically as in one of the foci, and then we are on the elliptical path going around the sun. Now, as I said, it's really close to a circle, so here the distance from the sun doesn't change that much because we're almost in a circular path. So this focus would be really close to the, I'm making a mess here. So the focus in a circular one is really close to the center, right? It's right. It's like the sun is at the center. There are two foci. Sun is over here on one of them, and we go around the sun. It's almost as if sun is at the center, but it's not, because the observations didn't match that. Okay, so for Earth, we are almost close to a circle. So closer you are to circle, then the closer the eccentricity is to 0. So this one eccentricity is like 0.66. This one is 0.98. All right. So find the equation of ellipse whose vertices are plus and minus 0, plus and minus 5 and 0, with eccentricity equals to 1/4. So right away, you know, the vertices are at -5 and 5. So let's just do it here. So here's -5, and here is 5. These are the vertices, right? And E, which is C over A, equals to 1/4. Now, if the vertices are here, then the center would be, oops, let me redraw this. The center would be in the middle. So the center is going to be HK is going to be just 0, 0, right? That's where that is. So that's the center. Now, to write the equation here, right away we know this is x squared over something plus y squared over something equals to 1. Now we need to find a and b, and we need to know which one is a. Which one is a? Well, first the vertices are horizontal, so a goes under x. A squared goes under x. So what is a? A looks like it's 5 units, right? So a is the distance from the center to the vertex. So that's a, so that's 5. So a is 5. So a squared is 25. Now what is b? Well, we don't know what b is, but we know the relationship that a squared equals to b squared plus c squared, right? Now we know a and we know e. So if we know e and we know a, in this proportion we can find c. So let's see. C over 5 equals to 1/4, right? So that means 4c equals to 5. So c equals to 5/4, right? So c equals to 5/4 from here. And since we know c, we can find b now. We have a, we have c, and we can find what? We can find b. So that's almost done. So let me erase this and show you the work here. So our b is going to be, so we set it in this formula right here. We know c is the square root of a squared. C squared is a squared minus b, right? That's the same as writing a squared equals to b squared plus c squared, right? If you move this to this side. So we know how to find c. We did c, 5/4. And now in this formula, we're going to put it and find what? So c is that. We put it in there. And then we find b squared equals to this number. So x squared over 25 plus y squared over what? Over b squared. You can leave it like that, or you can, multiply this and use it this way. But it's better just to leave it like this, because that looks like what? The form that we like. X squared over a squared plus y squared over b squared equals to 1, right? That's the equation for that. Okay, so let us continue with this. Now, one of the interesting characteristics of ellipse is that inside ellipse, if you're at a focus and you maybe shine a flashlight to the side of the ellipse, what happens is that it's going to reflect back to the focus. Now, they use that in architecture to create elliptical ceilings. You see this elliptical ceiling. So if you go in a room and the ceiling is elliptical, let's say you're standing over here and your friend is far away, depending how big the room is. In fact, there is one of these at University of Houston somewhere, Central Campus, and there are many others in all different places where the ceiling is elliptical. So if you stand on one side and whisper, the other person can actually hear you even though the person is far away from you, because the sound waves from your whispering goes in all directions and hits the ceiling, and they're all gonna accumulate where? right there. So that's one of the characteristics of ellipse. And these are called whispering galleries. All right, so we talked about the fact that we go around in an elliptical kind of shape, path around the sun. The sun in this picture is kind of in the middle of this, but this should be right here actually, kind of, right? Because it's really close to the center. But here, the picture puts it over here, should be about right here. Okay, now, it says the Earth's orbit around the sun is an ellipse with the sun at one focus and eccentricity is really close to 0. The length of the semi-major, now semi-major means what? Here is the major, semi means half of it, right? That means A, basically. So we are given A. The length of the semi-major axis is defined to be 1 astronomical unit, AU. So that's the unit of distance that you use in astronomy. So AU, unit of distance. So this is 1 AU, if we want to count everything in terms of AU. So the vertices of elliptical orbit are given special names. Now, aphelion is the vertex furthest from the sun, and perihelion is the vertex closest to the sun. So you see, if the sun is here, right, as I said, we have to move it kind of like there, then let's say the Earth is here. At any given point, there are two distances from this focus right here. As the Earth goes around, this distance changes, right? Now, when is it that the Earth is the furthest from the sun? Well, it's over here, right? Furthest from the sun. And then where is it that is closest to the sun? It looks like it is over here, right? It's closest to the sun. All right, so now it says here, find the distance in AU between the sun and aphelion, and the distance in AU between the sun and perihelion. Well, the distance from the sun to aphelion is about that much, and to perihelion is about that much. Now, how do we find that? Well, we know what E is, and we know E is C over A. Now we know what A is. Remember, A was what? A, half of this was 1. We're given here. So E equals to C over 1, so C equals to that, right? So distance from the sun to aphelion is A plus C, right? And so distance, so over here, the distance we want to find is A plus what? Plus C, right? This is A plus C. But that's far away from the sun would be A plus C, which is what? 1 plus 0.0167, which is that. And the distance, if the Earth is on this side, right, would be A minus. So this distance right here would be A minus C. And that distance is 0.9833. Okay? Now, of course, there is a misconception that the seasons come from what? The seasons come from the fact that in the summer you're closer to the sun, and in the winter you're far away from the sun. Of course, you know it's not true. The seasons have to do with the tilt of the Earth, right? So if this is the sun, and we are over here, when it hits, it's half of the sphere is lighted, right? But if you live in northern hemisphere and you're going around, well, you're gonna see the sun more than what? More than 12 hours. Because what? Because of this tilt here. So you see the sun more than 12 hours, and the angle of it is different. You're facing it. And in the winter is the other way around, right? So if you're in northern hemisphere, you actually see the sun fewer than 12 hours, and also the angle is different. So that causes the seasons not being close or far away from the sun. In fact, there's not that much difference, right? All right, so that's the idea of this application. Okay, next I want to talk about hyperbola and the rest of them, but I'm going to put this in another video. I'm going to talk about hyperbola and a parabola and rotation of axis and a little bit about polar form of conic sections. So we're going to do that in the next video. Okay, so let us end this video now. I'm going to come back and say bye to you. You can take care of yourself. I see you in the next video.